In a previous video, Nerds 96, I tried to use the 5370A from Hewlett-Packard to measure Allan deviation. And the results were a little bit questionable because I was using the wrong drive routine and could measure only very precise oscillators that were on the same frequency, because there was occasional loss of data, so the phase had to be constant over the entire measurement to make a lost data point disappear in the noise. Now I am using the right drive routine and compare oscillators that are not exactly on the same frequency. So the three traces on top here, red, blue and green, they are my Wenzel oscillator on 10 MHz. And what differs between the curves is that the oscillator is run from three different power supplies. So we can clearly see the noise in the range 5 seconds or 3 seconds up to, well, all the way. We can see the stability of the power supply is very important for the frequency of the Wenzel oscillator. And at short times, the Wenzel oscillator is far more quiet than the rubidium oscillator, which is a red trace. Here, a rubidium oscillator is the reference clock and the start input, while the stop input is another rubidium clock. So here I can see that the rubidium clock is much better than the Wenzel at times above 10 seconds. And I can see already at 2 seconds there is a small difference. But I know that the Wenzel is far more quiet at 0.5 Hz. So the instrument noise dominates, and below 1 second the only thing I see is the instrument noise, except for this red trace where the power supply is very noisy also at short times. This oscillator from CTI is noisy enough to overcome the internal noise of the measurement system with the 5370A. And this is the Wenzel oscillator I just talked about. From about 5 seconds, that's here, I can see the CTI oscillator high enough above the noise floor of the measurement system. I had to remove the rubidium trace because memory gets full, but it was a little bit below the trace here of the Wenzel oscillator. So in Linrad I can see up to about 20 seconds, so I should be able to reproduce these values. As it turns out, the Allan deviation plots are not very reproducible when I use this CTI oscillator. It seems to be because of variations in the air temperature surrounding the unit. So I paste it in this box and hope that it will not sense as easily when I, for example, walk by here in the room, or when small fluctuations in how the air is moving in the room. Here is the Allan deviation, now with the oscillator inside the box. On the left side we see the performance limit of the test system. That means the time uncertainty on the trigger points of the 5370A, as well as the phase noise of the reference oscillator, the rubidium controlled oscillator, which is rather noisy close to the carrier. And on the right side we see instability problems of some kind. And it's interesting to show that if I change from Allan deviation to Hadamard deviation, this looks much better. This is an indication that the problem is frequency drift. And that can be shown if we look at the frequency versus time. And unfortunately, there was a glitch at some point here that makes the scale compressed so we cannot see the frequency. I can select a range of time where there is no glitch, and then I can see clearly how the frequency is dropping. So now 10 hours or more have passed, and I make a new measurement. The new measurement is very similar to the old one. The curves are within the error limits. If I look for the Hadamard deviation instead, they are also very similar. I found out how to zoom in on the frequency versus time, and you can see clearly that the latest measurement is drifting upwards, while the previous one is drifting downwards. I guess this isn't really the temperature, it's something, a characteristic of the oscillator itself. I will make a couple of more measurements to see if it stays constant like this. Now I have measured the CTI oscillator 3 times while it is in the box, and the curves overlap within statistical uncertainty. And then I have connected the rubidium oscillator instead, so I have 2 rubidium oscillators, one as the reference and one as the test object. At short times, I see the oscillator is far more noisy than the CTI, and this is well known from other measurements. And then, at times above 100 seconds, one can see the difference between the rubidium and the CTI. Now, when I want to compare this with Linrad, I have the CTI still in the box, and I run a cable to the Linrad system. I can see that I cannot expect to see the noise from the CTI until I am above 100 seconds. But Linrad cannot measure above about 20 or maybe 50 seconds because it uses normal crystal oscillators, and one of them is not particularly good. Here is what I see in Linrad. I can trust results up to about here, because up to 20 seconds, maybe 30, I can trust the correlation. I don't know whether it has been running long enough, but the correlated spectrum is a little bit below the result for channel 1. And channel 2, which has a not quite as good oscillator, the evaluation gives a much higher value for the Allan deviation. Anyway, I can take notes. You can see here, when the oscillators are reasonably similar, which they are below 1 second, then the correlation is at a distance like that, below, and here it is even lower, but not much. But the oscillator in channel 2 suffers at very close to the carrier, 0.1 Hertz or so. I can read out numbers by clicking on a frequency. At 0.1 second, 1.06 times 10 to minus 12. When I compare Allan deviation as measured with Linrad and with the Hewlett-Packard time interval meter, this is what I see. I know that the region here has to be wrong. It's the noise of the instrument.
And I also know that this region is wrong because Linrad, the local oscillators, are too noisy to measure at 100 seconds. I think this region is correct if I have programmed things correctly, which may be true, but I don't know yet. I have not been able to prove it by this study. I also know that at 100 seconds the time interval meter is doing things correctly. And here, when the lines cross, maybe the truth is a little bit below here for a curve that looks something like that. Or maybe it looks like this. Anyway, this point is not right either, because I have a bandpass filter in Linrad that starts to remove data that is too far from the carrier. So actually what I have in Linrad is a modified Allan deviation. Maybe the truth is something like a line like that.